a bit of introduction about basically epistemology. You may have seen this XKCD cartoon. So empiricists versus mathematicians way over here in terms of purity and certainty over here. Once he published this, there was lots of other takes on this. So philosophers wanted to get in on that act. You've got epistemological philosophers, this is the one computer science was missing, so it's chucked in there. Maybe category theorists, I'm not even sure what they are. But in some senses, even you get into epistemological philosophers, when you're looking at foundations, how far do you go? And you're left with infinities in some sense. It's either turtles all the way down, or you're wrestling with infinities, and that's what I wanted to look at from a point of view of physics. So obviously Kalam makes the claim that there's no actual infinities, I reckon physics pushes back on that. In some senses, if you talk about infinities in physics and you want an empirical answer, you're trying to answer the question the wrong way. Okay, so by definition, you can't get a measurement of the unmeasurable. It's just there's not going to be an empirical measurement of anything infinite. And yet, in physics, all our foundations are mathematical, and mathematics the infinity is not a side feature; it's baked in to the foundations of maths. It's there, and when we come to our empirical observations, we bump into this everywhere. The infinities are a bit like whack-a-mole. If you knock down one, like you might get around singularities in a black hole, they'll pop up somewhere else. They pop up absolutely everywhere. So the first pushback on the Kalam is that actual infinities, it's impossible to know that they can't exist empirically, for a start. They are foundational in the mathematics that we use. They pop up everywhere. They pop up in the infinite sum on Feynman diagrams, many worlds interpretation. They pop up in internal inflation, other theories that try and get around this, like Wolfram's computation theory, very famously brackets all possible mathematics in terms of symbols, but in the end he gets to a system which has infinite dimensions, and again is way unobservable because it operates on a scale but below the Planck level. Anyone know what the Planck boundary is? Irish?
I'm not sure the exact number, but isn't the kind of sort of the smallest distance on the universe wedge the laws of physics are applicable?
Yeah. So we have two theories that are really good on every empirical measurement that we can make. They both have infinities baked into their mathematical structure, the mysteries. When we get to the Planck level, we get to a level where both need to be married together, but we can't make them talk to each other because they're saying something different about time. And at the Planck level, they're both saying something profound that we can't marry together. It's not, so the Planck level is like the limit that we can know something, but the universe hasn't got a problem with that. It goes below that. There's something happens, and there's many suggestions and mysteries about what goes in there. And Wolfram's his computational theory happens on scales well below the Planck level, and also it has infinite dimensions. Another place where it pops up is the horizon problem in cosmology. Do you know what this picture shows? Yeah.
That's some background radiation from the Big Bang, right?
Yeah. This is the Planck microwave background. This maps onto quantum fluctuations really, really, really well. Okay. So much so that we believe that Big Bang was caused by quantum fluctuations. Okay. Now, to get to this, to a whole universe, you need inflation. But the horizon problem is, as you go back in time, you have less time from the beginning to that point for things to interact. Okay. These points, let's say this point here and the point out here and there, just you have to imagine this as a sphere wraps around. So at opposite ends of the sphere, they're looking at opposite ends of the universe. This says that they were in perfect thermal equilibrium. Okay, so they interacted before anything had time to communicate with each other. So the horizon problem is that this either implies that you had an infinite regress of causal interactions that made it thermally balanced, or something like inflation. But then you have other infinities which come into inflation. If you have inflation in one place, you will find out it's really hard to stop. You get bubbles of universes and you get eternal inflation. Now, William Lane Craig, in his Kalam argument, uses a paper by, I can't remember the three scientists, but even in an inflationary scenario, you're because of entropy considerations, you're still left with a beginning. So most physicists believe in a beginning, and he believes that the beginning of the universe, so the Big Bang, is enough for his argument. I don't think he's applying it quite correctly. I want to get into that. So about the Kalam argument, can an infinite causal chain exist? So Kalam argues against actual infinities in causal chains, and argues against uncaused events. Now, the interesting thing about physics is that it allows for both of those. Okay, so and in a sense, certain events are both. So in quantum mechanics, to get the probabilities out of quantum mechanics, you need an infinite sum of all possibilities. You famously do it with Feynman diagrams. So Feynman diagrams are ways to sum all the possible interactions within a region of space. And there's different ways you can do it. There's some new ways to do it using geometry to really work out all the infinite sum of all the possibilities to create the probabilities that potentially actually happen. But then in that region of probabilities, anything can happen. So what actually happens, you could look at it as being completely free, uncaused, or as a result of an infinite chain of all possibilities that create the ground of possibility that then realizes in either a universe or radioactive decay or any other particle. So there's pushback on the Kalam. Mentioned a couple of others there. I won't go into those in details. Now, the thing that really helps me separate out this is Roger Penrose's framing. So Roger Penrose came up with this theory of conformal cyclic cosmology. The key thing he's wrestling with is why did the entropy start so low? So if the universe is just created by chance in all these possible states, the beginning point of the universe is the most probable configuration of matter, not pretty much imaginable. Okay, so you've got, this is from his book, so in order to produce a universe resembling one in which we live, the creator would have to aim for an absurdly tiny volume in the phase space of all possible universes, about 1 over 10 to the 10 to the 123 of the entire volume. This is the entire volume of phase space of all possible universes. For the situation under consideration. So you look back at our initial conditions, this is the probability. The pin, I mean, this is not drawn to scale, so it's like the conditions of our observable universe were massive. This is an unimaginably large number, by the way. It needs a bit more explanation. I won't get into the maths. So the point about this is that I've got a talk on entropy and Boltzmann doing online. I'll post links so you can look at that. But this says to me that the argument of creating a universe by chance is the worst possible argument for the existence of the universe, because things like Boltzmann springs are not just orders of magnitude more probable, they are so hugely more probable than getting a whole universe that probabilistically you're more likely to be a fluctuation in the quantum background that fluctuates with all your memories intact. That just fluctuating into existence by chance, and this instant being a millisecond old, is so overwhelmingly more likely than a universe that there must be something else going on. There's not a universe caused by chance. The idea of a universe caused by chance is the worst explanation. Okay, so that's so for instance, Richard Dawkins talks about climbing Mount Improbable. You only get up Mount Improbable because you fell off cliff impossible, and bounced. There's once you have really low entropy and a source of really low entropy, and in the initial universe that was the balance in terms of everything being perfectly smooth. And gravity wants to clump things together. That's the most improbable state of matter, is everything smooth. It clumps things, it creates points of order in the sky. You shine ordered energy on a rock for long enough with complex chemicals, you're going to get some really weird behavior that is way out of an explanation that just would get caused by chance, if that makes sense. Okay, so we're a result of this order that we see. Now, I want to get into, so his resolution of this is this cyclical universe. So for me, this is key when we come back to the Kalam argument. So there's a division in physics between massive particles, which experience time. So clocks. So to get a clock in physics, you need something that experiences time. You need matter, basically. You need massive particles. Photons don't experience time, photons of light. Geodesics, the gravitational field, doesn't experience light. There are massless bosons, force particles, that don't experience time because they are massless. Their alpha is their omega. They don't travel from A to B. All the laws of physics are time symmetric, and on that boundary, they exist. Okay, so they come into existence apparently, like I said, uncaused, but as a result of that infinite chain of computation of all possibilities, they exist. But that boundary, it exists at a certain point as you go back in the Big Bang. You get to before massive particles, and you just have basically photons in space-time, or plus the dimensions of the early universe. That's timeless. It's structured. It includes all the information in the universe. But before you get to what physics says is the singularity, where our equations break down, we're in this situation of light exists, time and space not being a thing that is experienced. Okay, you've got timeless light that is timeless and spaceless, and yet time and space emerges from that when you get massive particles. Now, that situation of basically timeless, infinite computation is the same before you get massive particles in the Big Bang, and after every particle has evaporated in the big black hole at the end of the universe. So infinite energy maps onto an infinite expanse of time after every particle has decayed. If you imagine an infinite space with just photons in it, they don't care that they're taking an infinite time and an infinite space to get from A to B or from alpha to omega, they are created at the end of infinity and the interaction with that last particle, massive particle in existence in the universe. And what Roger Penrose says is that conformally maps to the condition of the Big Bang. It's the same thing. So everything in terms of the massless particles, it's what's called the scale invariant. So at one end you've got infinite time in apparent space, but because you've only got massless particles, they experience the whole thing. There's no space for them. They leave as they arrive. It exists. That maps exactly onto the infinite density, because we're lost a measure of time and space now because we've got massless particles. So he says that you could imagine an infinite regress of universes. I think this is where he takes a jump, and he's basically got another form of multiverse, like a linear form. But for me, this is just the alpha is the omega, they're the same thing. Okay, whether that's an infinite chain or whether it's circular, or the alpha is the omega. That's just the way the universe is. Okay, it's baked in. Okay, now, so to come back to the Kalam, rather than say we're looking for a metaphysical cause of the physical universe, what does this say about an eternal physical cause that is existent? Okay, so you've got light and space-time as it is eternal, and timeless and spaceless, and in contact with the whole universe from the beginning to the end. And creation, the physical world, comes into being out of that. It's exactly like infinite computation of light in terms of all possibilities, limits itself for creation to exist. Okay, and this comes right back to a what theologians have said God is right from the beginning. So this is in Hebrew thought, in Kabbalah, you have I'm going to say this wrong, it's the Ein Sol, it's the infinite God who limits himself. There's the word for his limitation is tzitsum. So that's the by the limitation of the infinite, the finite can exist. Okay, so when I, as a physicist, look at that boundary, I'm not thinking metaphysical gods, Big Bang singularity existence. I'm seeing God in physical form is how I would imagine it, being all-knowing, literally, all-powerful, all literally, physical, embodied, but limiting himself for creation to exist. And so it's the creation in Hebrew thought is seen as this the infinite root restricting himself to allow creation to exist. So this is the one miracle that makes everything else possible. Okay? The one free miracle is the appearance of all the mass and energy in the universe and all the laws that govern in a single instance from nothing. The most improbable configuration of matter imaginable, and yet, if we thought, okay, what's the limit of, or beyond the limit of what we can imagine of what can be computed in terms of all thoughts, ideas, or whatever, that's what Big Bang. So with the Kalam, I would remap that. So you've got uncaused, which is not outside physics. We very much are looking at that, and the caused, the massive particles, but that infinite light of creation, I would say maps literally onto what theologians exactly said God was. And then you have it's not, this isn't a proof, this is, like I said, you can't prove that the infinite exists, but you have that experience of perception of the infinite, the divine. You've got that framework that underpins everything mathematically, it's there. And how you wrestle with that then, I think it goes into everything. I haven't covered everything I wanted to cover, but we've only got about 6 minutes left, and I want to finish without getting some feedback and questions. And if there was a glass of water, that would be awesome.
Oh yeah.